Thanks for choosing to come to this presentation. My name is Colin Flynn. I'm a geospatial data scientist at Dewberry. I've been working there for about 5 years now, and in geospatial work in general for 8. Today I'm going to be talking about using machine learning workflows to process big geospatial data. I have 2 examples that I'm going to walk through and just kind of highlight 2 different scenarios. So just starting off, big geospatial data. There's so much data in the world now. It's really hard to get an actual number on how much data. The most recent kind of estimate I could find was 147 zettabytes. It's not really that useful, but it's just a tremendous amount of data. And it's estimated that about 80% of data contains spatial information. So all of us geospatial people have to know what to do with all of that information. As sensors and other means of obtaining data become higher and higher resolution, the cost of storing that data is also going up. The resolution is better, so that's really fun, and we can derive more meaningful and useful products from it. But the storage just keeps going up, which also means processing times. Thankfully, in tandem, we get advancements in computer processing power and data storage, possibilities. This here is a seismal supernova sensor. We're using it to collect topobathymetric LiDAR data. And for example, right now, collecting data for the Florida Seafloor Mapping Initiative, we collect about 1 terabyte of data a day. And that's just raw data. It's not processed into anything. It's waveforms. So it's not even a point cloud yet. So it's an absolutely tremendous amount of data. But it's very high resolution, and it's very useful. So how do we handle it as geospatial practitioners? A big part is advancements in computer hardware. So everyone is at least now familiar in some part with artificial intelligence, and I think the common example is, of course, ChatGPT. That's not what we're talking about here. But it's all kind of building off of the same framework, which is in large part really built on GPUs, so graphic processing units, which are what makes computers able to play video games really well. It's also really good at matrix multiplications, which is what deep learning algorithms are doing in the background. The math is actually all really simple. It's just happening a lot of times in a lot of different layers. And GPUs are really useful for doing that. As well as parallel processing, so standard CPU processing. And those kind of all contribute. So we have these awesome advancements in AI and accessibility to AI solutions. So where even 10 years ago, if you wanted to do something with deep learning and you had a good GPU, you had to be able to programmatically build a full model kind of from scratch and create all the different tensors and elements and layers. There are so many open source options now for building a deep learning project. There's also, it's easier to find one that you can pay for that will help you develop one. So just being able to access those deep learning libraries for different programming applications is incredibly helpful. So this is, I think, an overlooked question in regards to artificial intelligence, is when to actually use it. And I think there's sometimes a thing that'll happen where you'll be in a project meeting and somebody goes, oh, we should just use artificial intelligence to do that. And that question comes to me. And a lot of times the answer is no. It's not always appropriate. The cost to spin up a deep learning model is oftentimes quite high. The adage, garbage in, garbage out, applies directly. You need a lot of good quality training data, and you need to spend a lot of time training a model. That's a lot of computer processing time, it's a lot of data time, or it's a lot of data storage. And sometimes it's just not the right solution. Sometimes it's faster to do a geoprocessing tool that uses more standard sort of operations. Sometimes it's faster to do things manually. But there are use cases where it makes a lot of sense to use deep learning. And we're going to talk about 2 of those examples. But before we get to those examples, there's kind of a decision that has to be made there where you can go open source and you can develop totally from scratch. There's a lot of Python packages and other programming packages at this point that you can utilize, or you can go with a more integrated software. So some softwares now have, we're ready to, you can train a deep learning model in our software. So there are different geospatial softwares that have those capabilities now. But a lot of times that comes with constraints in kind of customization, what the inputs can be, what the source resolution of your imagery can be, how that can be utilized. If you go open source, you have full control. It's a lot more work. So there's an explicit trade-off there. But they both have applications. So one example where we went full open source, utilizing open source Python packages like PyTorch, Lightning, and TensorFlow, we trained a a damage assessment model based on aerial imagery. So we've been working with FEMA on disaster relief since 1979, and we've been doing manual visual review damage assessments. So we had a large backlog of training data that already existed. So that initial hump of creating a bunch of training data was kind of already surpassed, and we were able to kind of jump in with our feet running, or hit the ground with our feet moving, and start training a model using all the data that we already had. So we used over 350,000 historic damage assessments. 350,000 is not a lot of training samples in regards to deep learning. It's a really good number to be at, but to have a successful deep learning model, you really do need a tremendous amount of input data in most cases. And so the kind of use case here is Hurricane Ian. So we were able to run that model that we trained. We've run it in other disasters as well, but but FEMA asked us to run it for this one specifically. And we performed over 4 million damage assessments. And the math there is if one person was doing it, it would take them 16 years. There's never one person doing it, but we were able to do that in a few hours. So as the imagery would come in from NOAA, from the Civil Air Patrol, and whoever was acquiring the imagery, we were able to run it and get those numbers back to the damaged homes back to FEMA, and that can expedite disaster relief to survivors. So it has a really direct impact. Another example, kind of more utilizing integrated software. So this example is all using Esri's deep learning frameworks. So they've integrated a lot of deep learning capabilities. And actually, when I was originally doing this, the contrast of control versus ease of use was there was a much bigger contrast. Esri's introduced a lot more variables now, and you actually have a lot more control than you originally did when training a deep learning model. But in this case specifically, and it doesn't really apply to the previous example, I like to think about it as an image science problem before it comes a data science problem. So before you're actually training a deep learning model, you really need to be thinking about what are you putting into the model. When you're working with Civil Air Patrol and NOAA data and it's the same 3 bands every time, you don't really need to be concerned with it. You have RGB. There's not really anything you can do with that. It's not 4-band, it's not multispectral, it's not hyperspectral. But this is LiDAR data. And if anyone remembers in their intro to GIS class when they had to do digitizing, remember that was really terrible, and you had to keep drawing all the points around the buildings? Well, that's how you derive break lines typically. So you have a LiDAR digital elevation model, and you have to manually draw the polygon for water bodies that meet the spec for that project. And so this is how we automated it. So we used Esri's deep learning frameworks. But like I was saying, the really important thing here is you can do point cloud models as well, but this is all based on LiDAR derivative products, but it has to match the LiDAR data. So what do you use as an input? And typically, people will look at things like a digital elevation model and a hillshade. An intensity raster is a lot of times a deliverable for LiDAR projects as well. And these are useful, but they're not that useful for training a deep learning model. It requires a lot more context. And one thing that's actually really helpful when you're training deep learning models for computer vision tasks, like extracting break lines from LiDAR data, is if you can look at it and you can visually tell easily, it's a lot easier to train a model. But you're not confined to just a digital elevation model or just a last return intensity. You can have multiple bands. You can create a composite image. And so it's hard to visualize all those layers, but you want it to look as good as you can visually to yourself and say, I can really see where water is all throughout this, and it'll really help. It gives you a good starting point for training a deep learning model. But there are other things you can create. So you can create derivative products. So derivative products from the digital elevation model. You can do a slope. You can do a roughness index. You can do a topographic wetness index. You can do. There's so many different topographic and hydrological modeling that you can do from a digital elevation model. So you can be creative with it. And like I said, you want to think about it as image science before data science. How are you deriving the inputs that you're going to feed to your model to best help it learn? How can you set up your model for success before you even get into the modeling? Then we get into some big data considerations. We were talking about the amount of data earlier. The example on the left is a model that was trained at 1 meter resolution for a 1,000 meter tile of LiDAR data. And it took 15 minutes to go from creating the raster and running the model, and it's only 183 megabytes. This one on the right, which looks a lot better, right? You can see the white outline is the prediction. So that's an unfiltered model prediction in each case. But it took 3.5 hours, and it's 6.5 gigabytes of data. So you do have to make trade-offs when you're kind of making those decisions of, okay, well, how much data are we going to put in? How much time are we going to put in? How much storage space do we have? But what sort of accuracy do we want in the end? And then kind of getting more into training a model and the sort of process that is. So you're going from an initial model, and you've maybe developed the inputs, and you think it'll work really well, but you always have to kind of move on to the next model. There's very much an iterative approach to training deep learning models, where you're going to review the results, and what are you going to change based on that? Are certain bands and image layers that you thought would be useful really not helping the model at all? Maybe you take those out, and you have a more compact model, and it's a little bit easier, and it takes less time to run. Or maybe you need to add more image bands in because it's not picking up on certain details in your AOI. And maybe you just need to add more training data. Like I said, the 350,000 examples wasn't really that crazy of a data set. It sounds like a big number, but in deep learning, more training data is better. There is eventually, eventually the curve level's off, but it's kind of hard to get to that curve. But then you can build on an initial model. You can use transfer learning. You can take the same model inputs, and you can try to apply it to a new area. Or maybe you're in a new area and there's new problems and you need a totally new model for the same objective, which is an example I have here. So we've run this process in Everglades National Park, which is incredibly complex hydrography. So we have very narrow features that we're able to extract completely automated. And then the example on the left is Copper River, Alaska. This is kind of as different of a geography kind of split as you can have. So from Alaska to Everglades National Park, we're able to employ the same technique, but it's a different input image. So it's a different model because the hydrography and the topography and everything there is so complex but different. The model just wasn't able to translate those geographies, so we trained a new model for the new area. But we're also moving towards standardizing a model and getting a model that's more agnostic to geography. So you can do that in a few different ways. You can try to find inputs that don't vary as much, where water is still consistently versus land able to be identified in a more simple manner. You can also include training data for different geographies. So you can include training data from Alaska and from Florida and from North Carolina and have a more geographically agnostic model. And then a comparison to kind of illustrate the point with automated versus manual is you're able to derive so much more detail. There's so much more data that you're able to derive from it. So a standard USGS project that has a spec of you have to collect break lines for water bodies that are 2 acres and above. That's pretty big. So you're losing so many small features, and that impacts the direct products. So that impacts the digital elevation model and what's used for flood modeling and all of those products. So this is coastal Louisiana, and we used a model there. And the NHD at the time of deploying our model was 12,000 miles of edge in our project area, and the predicted hydrography produced 43,000 miles of edge. So it's a dramatic increase in the amount of data that's present even after filtering and editing and the final product. And here you can see the level of detail that I was trying to illustrate here. So you have all these interconnected water bodies here. And rather than just the large features, you can see how much more complex the hydrography in the area actually is. And to kind of illustrate within that same scope the processing time, so we were able to do all of this coastal Louisiana project. It was 5,500 square miles. It took about 12 weeks for all of the raster processing and deep learning inferencing. And that produced such a large initial data set with 130,000 initial individual water bodies. And we used some filtering because this is a pixel classification model, so some of the classifications are incredibly tiny. So we want to keep things, and we're not filtering to that USGS spec of 2 acres. We're giving them more, and we're giving them more that is still accurate. We're not just unloading the model outputs. We're doing some programmatic filtering and dropping some predictions based on small size, and then we're doing manual edits on it as well. But the time for the manual edits is similar to the baseline, where we're manually deriving all of the 2-acre ponds and 30-meter streams and rivers. So we're taking the same amount of time in total to derive a much higher resolution data set with over 4 times the number of features compared to base specifications. And why it matters is you can map more smaller hydrographic features. So that gives you more accurate hydroflattening with less tinning and interpolation across digital elevation models. And then, of course, the downstream impact on modeling like hydrography, flooding, sea level rise. And I included this here because this is an accurate prediction. And that water body size is 0.04 acres. So you can see how fine of a resolution you can get down to. But this takes a lot of training data. And the composite images look really weird, but you can really clearly see, where water is versus where land is. That's it. Great. So there's only the imagery is input as a source of imagery. It's not really pixel to pixel. We're also using the historic building footprints, and so what it's doing is it's saying based on the area where a building is anticipated, what does the building look like? So it's using context that you can't really. It's kind of black box eventually, where it's just the context of the pixel or the image that it's creating around that feature. So it's creating an image for each feature, and then assessing that image. You had a question?
Since you have so many more water bodies digitized and they're so small, are you concerned with them being not permanent bodies of water, like they would dry up? You know what I mean? With the smaller bodies of water, if they weren't there all the time, like how often are you updating this data with the data that is not as you know what I mean?
Sure. Yeah. So the question is how, I forgot to mention the previous question. The question is essentially, how are we controlling whether or not the small water bodies that are well below spec are permanent? So we're not. So we're trying to match the source LiDAR data, because when people download the LiDAR data from USGS or from whoever is contracting the work, we want our break lines to match the source LiDAR, and ultimately the break lines just enforce a more accurate digital elevation model. So it's not meant to be authoritative in terms of this is where permanent water is. It's more so how can we derive the most accurate digital elevation model that we can. And in terms of flooding, typically if there's a large rainstorm and there's a much more water in an area, we won't fly LiDAR. We'll wait until it's a more normal condition. So there are certain ways that we mitigate things like that. But once it's in the data, we want to capture as much as we can from the data.
I like that you touched a little bit on the human element, because we've been utilizing models for over centuries, right? They're just calling it AI now.
Yeah.
And it is actually being adopted more into mainstream processes, like we're seeing in this example. I think it's really important, though, to acknowledge that there's still a human element in the validation of the processes. And I think it's good to include that in maybe some future presentations of yours. But just as an example, this is creating efficiencies within Dewberry, right, and how you're approaching those things. But it only gets you part way there, right? There still has to be that human manual editing of the final product.
Yep.
And I think it's just a good thing to talk about in the trade-offs. The Copper River is actually my contact. Take GIO for last. So I have experience with how the automation
Yeah.
can get you to a certain point.
Yeah.
But in the end, it really requires that manual eye in terms of validation and then improving future models and processes on your end, right?
Yep. So that's a great point. She's making the point that there is always a human in the loop, which is a great thing to keep in mind. And I tried to talk about it a little bit at the end with based on how long it takes to manually collect all of this data and then comparing it to collecting it with a model, but there's still human review. So that amount of time that does include human review, human edits, and it is part of the process still. But rather than analysts collecting everything and then another analyst reviewing everything. It kind of, we're trying to jump that first step and produce more data. But then, yeah, there's always a human in the loop. In any machine learning process that is done, appropriately, there should still be humans in the loop. Absolutely.
It helps with your final product, but then also it helps to improve your future processes.
Right. It feeds back into the loop. Exactly. Yep.
What type of models did you use and which ones were you based?
Could you clarify what you mean by like model architecture? Yeah, so the question is what type of model, and there's different levels we can get into that. It's not regression; it's a deep learning model, so it's neural networks. So, but then there's different model architectures. So, for example, the water body extraction model, I'm usually using a Deep Lab V3 model for the architecture. Yeah. All right, thank you all very much.